Hello, in this chapter, I'm going to introduce you about the vectors in 3 dimension. Okay, firstly, I need to introduce you what it means by vector in 3 dimension. So, as you learned before during your secondary school, okay, there is a xy axis, right? A Cartesian plane with xy axis. So, and let's say there is a point, is 2, 1, and this point 2, 1. The coordinates, we can write it in the form of position vector, means that it's a displacement from the origin to this point. Okay, so it's a displacement from the origin to this point. It's a direction, right? So it's a vector. So we can rewrite this point to be A, right? Vector A, or we can just write it as O to A. O, when we refer to origin, from an origin to a point, is actually namely this to be a position vector. It's a position vector. Any vector that start with origin means that the point is moving from, the displacement is from origin to that point. We name it as a position vector. Okay, it's a vector kedudukan. Alright, so we can rewrite this in 2 dimension as 2i. I is a unit vector for represent x-axis. Okay, it's in the direction of x-axis, a positive direction of x-axis, with the magnitude of 1 unit. Alright, and for this, then you know that they're going here 2 units, right? So 2 units. So, and 1 unit above. 1 unit above. So means that it's in the y direction. So it's in the direction of y. So which is positive j. This is a representation for a 2 dimension, okay, vector. So you can rewrite this as a column vector. In my lesson, all I was using column vector to simplify my way of writing the vectors. All right. So or I can using another form. All right. This 3 form is encouraged. We are encouraged students to using these 3 form. Okay, this is a three proper of writing a vector. Okay, either you write in column vector or in this form. Okay, so you see this is not a bracket, right? This is not a bracket, so it's a subspace. So if you look at this, this is for 2 dimension. So now we extend this chapter from secondary school. We move to 3 dimension. 3 dimension. So 3 dimension is actually x, y, and here to be z. So if 3 dimensions, of course, is a space. We usually refer to 3 dimension as a space. Alright, and this is a 2 Cartesian plane, and this line is on the board, right? It's on the board. But for this, let's say if I draw a point here, this point is actually not on the board. It's actually outside the board, means that somewhere floating around here, okay, in the space. So from here to this point, okay, to this point. So now for easy, so I just draw it on the board here. Actually is actually 90-degree perpendicular to the xy plane, okay, on top here, because there is a z value here. All right, there is a z value here. The value, for example, this point, I name it to be A, B, C. All right, A, B, and C. So definitely for the x-axis, there is a right, a value, and from the y will be a b, right? B, A, B, and the height here, the length here will be the c. All right, it will be the c. So it means that it's a 3 dimension. It's hardly for me to draw on the space. All right, so you know that this point is outside from the board. All right, so ABC. So usually we write this to be a vector A. Okay, let's say label this to be A. So or position vector for 3 dimension. So AI plus with BJ plus with CK. All right. So we have 3 component: component X, component Y, component Z. Okay, I is a unit vector for z-axis, J is a unit vector for y-axis, and K is a unit vector for z-axis. So then we have X, Y, Z. Alright, so we can rewrite this in column vector as well. So A, B, C, or write in the form of subspace A, B, and C. So then we have these two, for moving from 2-dimension to 3-dimension, you know that actually all the particles, the size is actually applying the 3 dimensions. Okay, let's move on. In the same video, I want to talk about how to find the length, right? The length of the or the magnitude of a vector. So, okay, for now, you look at this. Let's say this is your xy, right? It's to follow a Pythagoras theorem. Okay, to find the magnitude of OA, right? To find the magnitude of OA, it's just very simple. You're just taking the 2 square Pythagoras theorem, A square hypotenuse plus B square 1 square. Then you square root, right? So this is for 2-dimension space. And 3-dimension also we can apply the Pythagoras theorem. Okay, let's see what I mean here. Alright, okay, let's say if I have a point of OA, given that this vector is a position vector, which is 2i plus j plus 2k. For example, this is the position vectors. So how are we going to represent this vector in the 3-dimension space? So very simple. So we have x, y, and z axis. So which that 2 unit in the positive direction of x. So will be 2 units and 1 units for the y, right? J, 1j and 2k. So will be 2k. So means that the point is somewhere around here, okay? So here is 2, 1, right? 2, 1. And above here, from the space here, which is from here, we will have, okay, from this point to here. So in the two in 2-dimension x, y, you will see 2, 1, right? 2, 1 means on the xy plane, you will see it to be this will be z, alright? Z axis. So from the xz, you will see 2 and 2, alright? Means your eyes looking at here, it will fall on 2, 2, and from here onto the board, yz, it will look at 1 and 2, okay? So it's 3-dimension. So this vector is 2 units x-axis, 1 unit y-axis, and 2 unit z-axis. So I draw, can you see the arrow here? Okay. So this is a 3-dimension, right? So it's from this outside from the board, all right? It's 2, this point, this coordinate here is 2, 1, 2. In 3-dimension, we have x component, y component, and z component. Okay, so now I have represent this in the form of position vector, right? I'm going to explain to you what is meant by the magnitude, right? Magnitude. So I'm going to redraw a diagram to show you how to find the magnitude of a vector in 3-dimension. Alright, okay, I'm going to represent this by this diagram. I'm going to draw this vector from the origin to the point A, right? Origin to point A. So where's the origin to this point A? This vector is pointing out from the origin, right? From the origin to point A, and this will be the x displacement, right? If you look at here, it will be the x displacement, and this will be the y displacement, right? Y displacement. So this will be x, and this will be y. So your point A is actually 2, 1, 2, right? So it means this is 2 unit of x, 1 unit of y, right? So if you look at this triangle, this right angle triangle is on the is actually on the is somewhere around here. Can you see that? This is a right angle triangle where 2, 1, right? 2, 1. So you at first you should find the length. You want to find the length of this, right, in 3-dimension. So at first you find the length of this hypotenuse. So it means that the length of this from O to this point here, all right? O to this point, which is 2-dimension, right? 2-dimension, 2 and 1. So by Pythagoras, the length for this will be 2 square plus 1 square, square root, right? You're very familiar with Pythagoras. A square, the right angle, this is hypotenuse, right? Hypotenuse, the side opposite to right angle is hypotenuse. So 2 square plus with 1 square is the length, square root is the length for this, right? For this. Now together with this is also 2 unit. Do you know why? X is 2, Y is 1, and Z is 2, right? 2, 1, 2. The height here is 2 because the Z is 2. So now Now we look at this triangle. For this we have done. We have find the length for this. Now we're closing this. Then you can see here there is a upper right angle triangle, right? Which I know the length here is square root of 2 square plus 1 square. 2 square, 2 square, right? This is 2 square, which is 4, right? 2 square, which is 4. And this is 1, right? 4 plus 1. So 4 plus 1, you have 5, square root of 5. Means that the length for this is square root of 5, alright? Square root of 5. Now I want to find the length for the magnitude from O to A. Now it's finally we want to find the magnitude from O to A, right? O to A. So very simple. Apply Pythagoras again. Means that we apply 2 times Pythagoras, 1 time and second time for 3 dimension. So then for this we going to add up square root of 5 square plus with square root of 5 square plus with 2 square, and we square root. Then we have square root of 5 square, you're getting 5, right? Plus with 2 square, 4, which you're getting square root of 9, which give you 3. Means that the position vector, the position vector from O to A actually give you the 3 units, the magnitude of 3 units. Alright, these 3 units is actually can find by doing this way. A faster way will be you taking 2 square, 2 square plus with 1 square plus with 1 square plus with 2 square. You can join them all together. The x square, y square and z square all join together. This is actually the coefficient of the I, j and k, right? 1, 2. So if you get 4 plus 1, 9. You're getting 3 as well, right? So means that we can actually finding the magnitude of a vector in 3 dimensions by using this method here. So now I'm going to summarize for you the formula for magnitude of a vector in 3 dimensions. Alright, I'm going to summarize here. Just now I'm using origin to this vector B, right? So vector A. So now actually this formula for magnitude can be applied for any displacement vector, okay? Either it's position vector or displacement vector is applicable. Because if I said moving from A to B with xi, yj, zk, the meaning is x unit, right, of x-axis, the x unit. So and y unit and the z unit, right, is moving in this way, right, going to the right, going up and going up again. So we will say that this to be okay, we're saying that this to be a vector, is a displacement vector. So then we know that there is an x unit. Before how we move from A to B is actually for the x-axis we're moving x unit, for the y-axis we're moving y units, and the z-axis we're moving z units here, right? Based on the Pythagoras, the length for this will be square root of x square plus with y square, the square root of x square plus with y square, the hypotenuse, right? So finally, we want to find the magnitude of AB. We apply Pythagoras 2 times. 1, 2 dimension. Okay, now we're going to apply, now become this AB, become the hypotenuse. This is right angle, hypotenuse for these 2 sides. So means that we're taking this square root of x square plus y square. We go and square it plus with z square, right? Plus with z square. So we square root everything here, right? For this a square, we're taking the square root of x square plus y square, we square it, plus with the z square, then we square root everything here. So finally we get the formula, right? Which will be square root. If you square, you're getting x square plus with y square plus with z square. So this is the formula for magnitude for any vectors. Alright, either it's displacement or position vector, this formula is applicable. So it means that the length from A to B, magnitude is actually the length of the vector. So which is the square root of the sum of square of all the coefficient for x, y and z component, alright, of the vector. So I hope you understand. So we will go examples to discuss about this. Okay, later on in the examples from the video, we will discuss about how to finding the magnitude of a vector. Alright, I think that's all for this video.